So here's the algorithm. So this is the training function. So we have here, so this is our data set. This is the max iteration. We're going to discuss that later. So initially we are going, so again, this is just a very simple implementation of the perceptron algorithm. So it, you would expect this to not look very advanced. So these are the weights. We are going to initialize all of them to 0. There are also other training functions where based on the data set, based on the information gathered from the data set, we can initially provide more reasonable values to our weights instead of just initializing them to 0. Because from the data set, the data team would have studied it beforehand, and they would like provide information that, hey Chris, this feature is this feature would have a lot of weight because it influences the decision a lot. So yeah, so for simplicity, for now, we're just going to initialize them to 0 and the bias b as well. So the max iteration here is just so here's the main training code block here, and then we're just going to repeat this block here based on the iterations we have set here. So let me just pull up my eraser because I messed this up. But yeah, we're going to discuss about more about the iterations here, but let's just focus on these lines 4 to 9 or to 10 first. So for all examples, so an example is just feature values. We have x, so the x is the input, and the input will have x sub 1, which is the feature value of feature or the first feature, and so forth. So we could have an input with, let's say, 10 dimensions. So 10 like for 1 dimension, 2 dimensions, 3 dimensions, we can think, like we can still imagine that. Even 4 dimensions, somehow we can still imagine what that would look like. But vector with a 10 dimension, I don't think so. So that's the input x, and then the y is the label. So basically, since this is a training data, we know we have the input and we know the output, the outcome for that, either positive or not. So the label here is either yes or no, and that is our y. So for each example in our data set that is provided as an argument, what we're going to do is we're going to get or compute for the activation for that specific example. So again, using the formula we've got before, so it's just the summation. Oops. I know this is kind of bit of dragging, but bear with me. So this is the formula we got before. So here's the summation, and then we added the bias. So compute the activation, and once we get the activation, we need to know whether we got the correct activation or not. So this is the actual activation of the example. So actual activation. So it is either -1 or 1. And that is also our label. So as we compute the activation for this example, so given the x, we compute for the activation, and mind that initially our weights and bias are 0 or perhaps set to other values. So we would there's no certainty that we get the same activation from the input x with the actual activation. So there's no guarantee. So we need to know whether we got the correct activation, because if we don't get the correct activation, then certainly we have to adjust our weights, right? So we have the assumptions of our weights. Like we have the assumptions that this specific feature influences the decision heavily towards the positive activation, and this other feature as well influences the decision towards the negative activation. So we have those assumptions. We tested those assumptions to this input x, and then if we see that the activation we computed from those assumptions is not the same to the actual activation, so there must have been something wrong with our assumptions. So that's why we have to correct those assumptions and adjust the weights. So a simple trick to know whether we got the correct activation or not is just to multiply the activation we got to the actual activation, and then if we get a positive, then we would know that we got the correct activation. So for example, if the actual activation is negative and then our computed activation is also negative, then we get a positive result for this one, and positive times positive is also positive. So when we get this is just a simple trick to determine whether we got the correct activation or not. Now when we got the wrong activation, this is where we need to adjust, and the way we can adjust the weights is just to multiply the label to the feature value of that, because we are going to so since x here has multiple feature values, so for each feature value we're going to update the weights, and since y is just positive or negative, and then the feature value could be some specific value, then it will just, so the idea here is like mathematically viewing this, the weights is updated by, so we take a specific weight, we add the current value of the weight to the value of that specific feature corresponding to that weight or feature, multiplied by either negative or positive. So it's just like the idea or the concept is, so we got the wrong activation, and so since we got the wrong activation, we need to adjust our weights, and the way to adjust that is, it's just like, so since I got the wrong activation, so how would I update this weight? Perhaps we can look at this thing here. So this is the feature value, and this is the label, so either negative or positive one, right? So since we got the wrong activation, we would think that maybe this value here, maybe this feature value here influences our decision either towards negative or positive. Perhaps this feature has a high influence to our decisions, and how it would affect or influence the decision depends on its value. And then to where either positive or negative, to where to know whether this feature value influences the decision towards the negative or positive is determined by the label. So if we get a label of negative, so let's say an example, we got the example, the label is negative, and then we got the wrong activation, so we get the feature value of that specific feature and determine whether it influences towards negative or positive, so we multiply it to the label. So that is just the purpose of this term here. And then we also update the bias, and then we do all this to all the examples, and then after we iterate over all the examples based on the max iterations we provided here as an argument, so let's say we put here 3, so it would again iterate over all the examples 3 times over and over again. So it would update the weights and the bias a lot more to achieve the sort of the desired values of the weights. And so once we got the weights, once this iteration from here is finished, then we return the weights. So that is just the basic concept of the algorithm.